In the last video, we covered Morse code as a relatively slow introduction to communications. However, given that watching this video right now requires at least 25 million times the data throughput per second that I could manage with my fingers, a time compression is needed. From now on, computers and electronics will control the signals, not us. So let's explore how we could implement a protocol to communicate that can be easily automated and operate at a decent speed. First, we need a code for our data. Computers are quite good at dealing with ones and zeros by their nature. This means that it's probably most efficient for us to encode our data in binary. Whether letters or numbers, there's a standardized method to encode them into binary. For letters, we have ASCII, a standardized mapping of characters to binary. For numbers, we have base 2, fundamentally synonymous with binary. Additionally, electronics are quite good at telling voltages apart, and in this case, we will say that 0 volts, ground, indicates a 0 bit, and a higher voltage state indicates a 1 bit. This is called a non-return to zero line code, or NRZ. This sounds a bit weird since it is returning to 0 volts. However, the alternative in this case is having our 0 voltage being negative, but then returning to 0 before the next bit, which could be another negative pulse indicating a 0 or a positive pulse indicating a 1. Right, now that that's sorted, let's say I want to transmit a character code corresponding to the letter lowercase a. There's a problem though. If I was on the receiving side, I would have no clue what the signal meant. Which of these was ones and which were zeros? Are they even done transmitting, or is this more zeros? This is a tricky problem to fully overcome. To try to fix this, we can use another board to set the time like a metronome so that we can agree where our bits are. We will use a consistent square wave signal that allows us to coordinate transmission and reception, called a clock. Now we can transmit data. This is a working, bare minimum digital communication protocol. We can transmit that lowercase a again, and it can make it out to the other side. This isn't quite satisfying though. Firstly, we can only transmit to one target with this protocol, since we would end up transmitting to all other connected devices. Second, we have no way of knowing if anyone is listening on the other side or not, which is often quite important. And third, the start and end of our message is not defined well enough. We could assume that the message is over when the clock stops, but there ought to be a more stable way to do this without adding much more complexity. To deal with the first problem of not being able to transmit to multiple devices at once, we can name our devices, giving them addresses. The controller, the one sending out the message and controlling the clock, doesn't need an address, but we can numerically label our peripherals, the devices connected to the controller. We don't want to bother decoding the signal on peripherals that aren't interested in this, so we can put the address of our data out front. That way, all peripherals can listen to the address, and if it's not them, they can ignore everything following it. Note that the address is only 7 bits versus a more traditional 8. We are also going to add a bit to say whether we are writing data to the device, a 1, or reading data from it, a 0. That way, the peripheral can know to switch roles for a moment and begin to talk back to the controller. In the same stroke, we can solve the ambiguity problem. Notice that there's room for 1 bit between the address frame and the data frame, and 1 at the end. We can use that room for an acknowledgement to prove that the peripheral addressed is present and ready to receive, and to say when a controller is finished receiving data from a peripheral. We will set this solution aside for a second and worry about the third problem, the start and end conditions of our signal. When looking at this problem, we can take a step back and look at the big picture. We have 2 wires, comprised of 1 clock wire and 1 data wire. How can we make a signal that is not ambiguous that could be used to signify the start and end of a transmission? Let's add some hardware to the mix. We can add pull-up resistors to the data and clock wires, which means those lines will now default to the high voltage level rather than floating uncertainly or being stuck low. Now, the hardware to transmit a signal can be simplified, as it only needs to be able to connect the wire to ground, rather than to be able to connect it to ground or connect it to the high voltage level. It can simply let go of the line to allow it to go high. Most important to our problem, however, is that it allows us to make a simple and unambiguous start and end position. Prior, the data has always changed before and after the clock, but never during, as to prevent ambiguity. However, we can use this state to signal when we have begun transmitting and when we have stopped. For beginning a transmission, we can bring the data line low while the clock is still high, and then bring the clock line low. Then, the beginning of the address will be transmitted and the clock will begin again. When we are done, and the transmission is over, we can let the clock go high first while the data is still low, and then release the data, thus resetting the lines to their initial state and unambiguously signaling the end of the transmission. In the same stroke, we have also simplified problem 2, as all the peripheral needs to do to let the controller know that it is listening is to pull the line low during the acknowledgement bit. A high acknowledgement bit tells the controller that the peripheral is either unwilling or unable to receive data, whether it is disconnected or busy with other things. This also allows us to put our data in a sandwich of acknowledgements, in this case 8 bits wide. If we want to transmit more than 8 bits, we can simply continue transmitting after the second acknowledgement, continuing with another byte and an acknowledgement until we are done. At last, a working interface. Let's demonstrate again with the lowercase letter a. I can enable pull-up on the controller TixBoard, which makes the lines default to high. I can then switch both controller boards and the data line peripheral to low. First, I will bring the data line low by switching the input to output, followed by the clock line. A message has begun. Next, I can transmit the address bits, making sure to pulse the clock before changing state, as to prevent unintended signals. The acknowledgement bit can be pulled low by switching the data line peripheral from input to output, moving the clock, and then returning the line back to the controller. Then the data, simply the lowercase letter a. And a final acknowledgement. Seeing as the receiver has agreed to more data, we could carry on with another 8 bits of data, but we are done for now. So we can release the clock line, and then the data line, finishing our transmission. This is close to the modern interface that is usually generically known as the 2-wire interface, but is in fact a simplified version of the I2C interface. Let's add some bonus features to bring it mostly into specification with I2C. First, let's tie up a loose end from earlier. Remember when we added the ability for multiple controllers on one line? Well, that was missing an important bit of logic. The controllers are smart enough to know when they've already seen a start indicator and not begin to transmit until they're done, but what if they begin to transmit at the same time? Well, we need to decide who gets to talk. Since there's only 2 lines, we must choose. What we can do is we can watch the line voltage on the data line and compare that to what we expect it to be. Consider the case in which both controllers begin a transmission at the same time. Let's also assume that they are transmitting to 2 different peripherals with 2 different addresses. If one of our controllers wants to have a 1, leaving the line high, and the other wants it to be a 0, the 0 will always win by virtue of the hardware design. This tells the controller that wants to have a 1 in that position that another controller is talking, and it will back off the clock and data lines and wait for the stop condition before sending its data again. This implicitly means that the lowest addressed peripheral will win the process, called arbitration. However, if they are addressing the same peripheral, the arbitration will run into the data bits, but will functionally operate the same, watching for a difference between the expected and actual operation, waiting for a difference, and dropping out as soon as it notices a difference. Let's add another detail. Let's say that the peripheral is in the middle of receiving data from a controller, and it wants to pause the transmission momentarily, and then resume it when it is done with whatever it needed to do. We can allow the peripheral to hold the clock line low, called clock stretching. The controller, noticing this in the same way it noticed arbitration, will wait until the peripheral releases the clock, keeping the current data bit in the same position until the clock is released. Once it is released, the controller will wait a moment to allow that data bit to be processed by the peripheral, and then continue. It's worth noting that clock stretching will incidentally occur when 2 controllers attempt to transmit at nearly the same time, with the low state of one's clock notifying the other device that it needs to wait to begin the high period. Once the first controller releases the line, their high periods will begin simultaneously, implicitly synchronizing their clock signals. One final addition: what if we needed more addresses? Well, we can provision for this logically. In the I2C protocol, there's a few reserved address ranges, and we can use one of these, in this case 11110, to refer to the expanded 10-bit address space. Then, since we have 2 bits left, we can do the 10th and 9th bit in the traditional address frame. The read and write bit will operate the same, and the acknowledgement will be performed by every device with a 10-bit address that starts in the 10th and 9th bits. Then, in the first data frame, the other 8 bits of the address are enclosed, followed by the acknowledgement of the address device, and continuing with more data bits. This is the high point of the I2C specification, which is available in full online from NXP. Bits and pieces have been omitted for the sake of brevity. We can see it in action using an oscilloscope in a test setup I've made. On the screen, you can see the electrical signals of the I2C going from one test device to another, in this case 2 Arduinos wired together on a breadboard. Here you can plainly see the I2C protocol in action. We can trigger the scope to make it hold still and zoom in for a closer look. First, the start condition is apparent with the data line falling before the clock. This is followed immediately by the address of our peripheral, which I have voluntold to be 24 and is decoding in hex to 2A. We are writing to our peripheral, and the peripheral agrees, beginning the data byte. This is set to simply count up between 0 and 255. The peripheral agrees to more data, but we are done, and the stop condition will occur. We can also try reading data like this. The peripheral is just counting like the controller was in the last example, except this time the controller decides it is heard enough after the first byte, lets the acknowledgement go high, and finishes the transmission. The elegance of the solutions enclosed in I2C cannot be understated, and it sees very common use in communication between integrated circuits, sensors, and anything else that knows how to speak I2C. If you made it the whole way to the end, congratulations. If there's a follow-up, it will be in the end card. If not, it'll be whatever YouTube thinks you want to see.